In this video, we are going to discuss about RLC series DC transient problems. First problem is find I of t and maximum current for the circuit shown below if the switch is closed at t is equal to 0. This is the network, so that at t is equal to 0, this becomes a circuit, so that current I of t will flow through the circuit. In order to solve DC transient problem or any transient problem, it is convenient to transfer this T domain network into S domain network like this. So this 10 volt become 10 by S, 1 is nothing but 1 itself, and this inductor become 0.25 S, and this capacitor become the corresponding impedance form in S domain is 1 by Cs, that is 1 by 1.33 S. Here, as initially the switch was in open condition, initial current through the inductor and initial voltage across the capacitor is 0, assumed to be 0. Now, after converting this T domain network into S domain network, we can easily write down KVL equation over here. Here the KVL equation becomes 10 by S minus I of S, we can take common, I of S into 1 plus 0.25 S plus 1 by 1.33 S is equal to 0. Again, multiplying entire thing with 1.33 S, we can write down in this manner 10 by S minus I of S into 1.33 S plus multiplying these two terms, we can obtain 0.3325 S plus 1 divided by 1.33 S is equal to 0. Again simplifying, we can write down I of S as 10 into this one, that is 10 into 1.33 S divided by S into this part, 1.3325 S square plus 1.33 S plus 1. From here we can cancel S and S. So after again simplification, we can obtain I of S is equal to this one, that is 13.3, all divided by, from denominator we can take the quotient of S square outside, it become 0.3325 into S square plus 4S plus 3. So when we are doing this simplification, we can obtain this part as 40, and we can factorize this denominator as S plus 3 into S plus 1. Now we can easily solve this problem by using partial fraction expansion. This equation can be written as I of S is equal to A divided by S plus 3 plus B divided by S plus 1. A can be obtained by multiplying S plus 3 with this equation I of S and equating S is equal to minus 3. After solving, we can obtain A as minus 20. And similarly, we can obtain B by multiplying S plus 1 with this equation and equate S is equal to minus 1 into that. After solving, we can obtain B is equal to 20. Now we can substitute the value of A and B like this in this equation. And since 20 is common, we can take 20 outside. So I of S is equal to 20 into minus 1 by S plus 3 plus 1 by S plus 1. Now we can easily find out L inverse in order to find out I of t. After taking L inverse, we can obtain I of t as 20 into minus e raised to minus 3t plus e raised to minus t ampere. Now we got the first part of this problem, that is I of t. Next part of this problem is to find maximum current I max. At any maxima or minima condition, the derivative of this with respect to variable is equal to 0. So in order to find out the maximum condition, we can find out derivative of I with respect to time and equal to 0. From that, we can obtain the time at which maxima occur. Then we can substitute that time in this expression of I of t, then we can obtain maximum current. That is, at maximum current, di by dt is equal to 0. So di by dt of this is equal to 0. So in order to find out the derivative of this part, this 20 we can take it outside. Derivative of minus e raised to minus 3t is minus e raised to minus 3t into derivative of this, that is minus 3, plus e raised to minus t into derivative of minus t, which is equal to minus 1, which is equal to 0. After solving, we can obtain the expression as 60 e raised to minus 3t minus 20 e raised to minus t is equal to 0. Further simplifying, we can write down 60 e raised to minus 3t is equal to 20 e raised to minus t. So 60 by 20, that is 3, is equal to e raised to minus t divided by e raised to minus 3t. It can be simplified as e raised to minus t plus 3t, which is equal to e raised to 2t is equal to 3. After solving, we can obtain time at which maximum current occurs as 1.5493 seconds. Now, into this current equation, we can substitute this time so that we can obtain maximum current. So, after substituting t as 0.5493 in this equation, we can obtain I max as nearly 7.7 ampere. So, this completes the solution of this problem.